Okay, let's talk about effective nuclear charge. Now, you know that the nucleus has positive charge, and this is because of all those protons that are in the nucleus, and they attract the electrons. So there's some electron that is out here being attracted to that nucleus, but there's something in the way. And the thing that's in the way that prevents this from being a full-on positive charge due to the electrons are what we call the shielding electrons. And these are just the electrons that are effectively in the way. They interfere with this attraction between the number of protons in the nucleus and the electrons that are furthest away from the nucleus. These would be what we call the valence electrons. And if you remember, the valence electrons do chemistry. This is where chemistry happens. It's in the valence electrons. So this thing that we call effective nuclear charge, and we just call ZeF, is equal to the number of protons that are in the nucleus minus the number of shielding, that spells shielding, believe it or not, the number of shielding electrons that interfere with this connection between the nucleus and those outer shell electrons. So effective nuclear charge is the ZeFF. The number of protons we just call Z, that's that term right there. S stands for the number of shielding electrons. Those are the number of intervening electrons between the nucleus and the electron of interest. That's generally going to be the valence electrons, the ones that do chemistry. And it just says this: the positive charge experienced by the outer shell electrons is always less than the full nuclear charge because the inner shell electrons partly offset the positive charge of the nucleus. Okay, so they get in the way. And so here is my little analogy. We look at the light bulb on a summer evening, which is coming up soon, and since we're all locked in our houses, we're going to be looking at the light bulbs. At any rate, and what shows up are bugs. But we're going to think about the light bulb as being the positive charge in the nucleus and some number of protons in the nucleus. Now, the electrons or bugs that get to the light bulb first, they prevent these outer shell electrons from feeling full positive charge. It's sort of like they're casting shadows. That's my analogy, for better or for worse. Use it or let her go. But that's what we're talking about here, all right? So these inner core electrons, they partially neutralize this positive charge. So these electrons, they're just not feeling the love, all right? So let's talk about periodic trends. Within each group, the atomic radius tends to increase from top to bottom, and that's just really because the electrons that are, as you go further down the periodic table, we're going from n equals 1 to n equals 2, n equals 3, n equals 4, and so on down the periodic table. And you remember what n stands for. That is the principal quantum number. And the principal quantum number tells us the distance that the electrons are from the nucleus. So as you go down the periodic table, the electrons are getting further away from the nucleus. And that distance away from the nucleus, guys, that is telling us how big the atom is. So the further away the electrons are from the nucleus, the bigger the atom is getting. So as you go down the periodic table, atoms are getting bigger. Okay? Within each period, the atomic radius tends to increase, moving from this direction to this direction. That's a little harder to understand, but we're going to understand it within the context of that equation that we gave you, which says the effective nuclear charge is equal to the number of protons in the nucleus. That's the Z that you had. That's the Z factor minus the number of shielding electrons. And we'll just call these core electrons. Any electron that's in the core that is not a valence electron could be considered as shielding electrons. All right? So here's our explanation for that. As we go from this side of the periodic table to this side of the periodic table, what is increasing is the number of protons. Okay? The number of protons is increasing. And if the number of protons is increasing, this is getting bigger. And since we're at the same in-principle quantum number as we go across, this is 2s, this is 2p, everything that's in the core is still, the highest energy is at n equals 2, but the number of protons is increasing. So as that number of protons increases, that attraction for those outer electrons gets stronger and stronger and stronger, and so the atom gets smaller. So on this end, the atoms will be smaller, the smaller radius, and on this end, they're going to be larger because you have fewer protons in the nucleus. Okay? So the trends are the the atomic radius increases as you go from top to bottom. It increases going from this side to this side. I think an easier way is just to say this side is small and this side is large. And when I'm talking about small and large, I'm talking about size. So small, large, okay? And what we're talking about here is the radius. And as you go down, this gets bigger. As you go from left to right, this gets smaller. And that's because the increasing number of protons in the nucleus. Okay. All right. So here are the measured values, the experimental values for the atomic radius. And you can see this is in angstroms. An angstrom, 1 angstrom is 10 to the minus 10 meters. So we go from 0.37 angstroms. Here's lithium. This is all group 1 going down here, and you can see everything's getting bigger, 1.34, 1.54, 1.96, 2.11, and so on. So the atomic radius is getting bigger, going from top to bottom. Remember, this is n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and so on. And as you go across the periodic table, okay, we're still at n equals 1 over here. For helium, it's 0.32 angstroms versus hydrogen's 0.31. Helium is a little bit tinier. Why? Because there are 2 protons in the nucleus which pull its valence electrons at n equals 1 tighter, closer to the nucleus. Okay? So helium is actually smaller than hydrogen. Lithium is larger than beryllium, which is bigger, larger in atomic radius than boron, than carbon, nitrogen. And neon's over here at 0.69 angstroms, whereas lithium is way over here at 1.3 angstroms. Lithium has 3 protons in the nucleus, and neon over here has 10 protons in the nucleus, but they're all at n equals 2. So as you go across the periodic table, the radius is getting smaller. Okay, which of the following atoms has the largest radius? So here's the way you do this. You compare 2 at a time. So we're going to compare nitrogen to arsenic. We're going to pick a winner and throw out the loser. And we're going to just use our trends. So we're looking for the largest radius. Nitrogen is up here. Arsenic is down here. Our trend is, as you go down the periodic table, the atoms get larger. And so arsenic is larger than nitrogen, so nitrogen is the loser. Arsenic is larger than nitrogen. Now let's compare arsenic to fluorine. Well, here's fluorine way up here. It's both higher and it's further to the right, so fluorine is definitely smaller than arsenic, so fluorine loses. Nitrogen's already lost. Fluorine loses. Arsenic is still the winner. So we cancel fluorine. Now we're going to compare arsenic to bromine. This might be a little bit more complicated. Here's bromine over here. We're just going to use our trends. And our trend says, as I go from this side, the radius is smaller. There's more protons over here. And so arsenic has fewer protons. We're still N equals 4 level. This is a 4p3 and then 4p5. Bromine has 2 more protons in the nucleus than arsenic, so bromine loses. Arsenic is the winner. Arsenic, or B, is the largest atom in that series.